Everyone, welcome to my YouTube channel. Let's solve this problem, which is a leetcode 169 problem, which is called majority element. Let's read the problem statement. So given an array nums of size n, you have to return the majority element. Now what is majority element? Majority element is the element that appears more than n by 2 times. You may assume that the majority element always exists in the array. So they have given one example here. 3 is appearing 2 times, 2 is appearing 1 times, right? And the number of element, what is the n value? N value is 3. So when we say n by 2, so n by 2 is 3 by 2, which is nothing but 1. So if an element which is coming more than 1 time, then that element is a majority element. So here one element is coming more than 1 times, that is 2. So now here the 3 is the majority element, so the output is 3. Let's take another example. So how many times 2 is coming? 2, 3, 4. So 4 times 2 is coming. How many times 1 is coming? 1 is coming 3 times, right? And the number of element is 1, 2, 3, 4, 5, 6, 7. So n is 7 here. So when we do 7 by 2, which is nothing but 3. So if an element which is coming more than 3 times, then that element is a majority element. So here 2 is the element which is coming 4 times, so the majority element is 2. I hope you understood the problem statement. Now what can be the brute force approach to solve this problem? What can be the brute force approach? So just like we have did here, what we can do, we can count frequency of each element, right? We can count frequency of each element. We can create a hash map and we can count frequency of each element, right? And we can store that frequency of each element. Now what is the time complexity of that? Time complexity is order of n, because we are iterating the entire array, so the time complexity is order of n. What is the space complexity? Space complexity will also be order of n. Why? Because we are storing each element in the hash map, right? In hash map. So if you store each element in the hash map and there are n elements, so the space complexity will be order of n. So this is the solution for this is the time complexity and space complexity for the brute force approach. Can there be an optimized approach? Is there an optimized approach? Yes, there is an optimized approach. Let's talk about the optimized approach. This is very important algorithm. This optimized approach is also called as Buyers-Murray voting algorithm, right? What is this algorithm? Let's talk about that. Let's talk about this algorithm via example. So let's say the array that is given, that array is 2, 2, 1, 1, 2, 2, 1. Let's say this array is given to us, right? Now let me do indexing quickly. 0, 1, 2, 3, 4, 5, 6. Now what does Murray voting algorithm says? It says that let's take a candidate, right? Let's say there is a candidate and let's assign the candidate to the first element. So here the first element is 2, and then what you will do, you will store the count of that candidate. So there is another variable called count and initialize that count to 1, right? And traverse the array, and if when we are traversing the array, we will start traversing from I equal to 1 till n time and check whether the array of I is equal to candidate. So if array of I is equal to candidate, then we will increase our count. If it is not, then we will decrease the count, right? Till when you will decrease? Till the count becomes 0. So if the count becomes 0, then we'll update the candidate as well. So let me do the run. So here when I is 1, this array of I is equal to candidate, right? So we will increment our count variable to 2, right? Now I is updated here, I is at 2. Now array of I is 1 here, but the candidate is 2. So these two are not same, right? this and this are not same. So what we'll do, we will decrement the count. We decrement the count, so 2 will become 1. Now I will move ahead. Now see, again this array of I is not equal to candidate because candidate is 2, right? So we'll decrement the count to 0, and when the count will become 0, then what we'll do, we will update the count, we will update the candidate with the array of I. So here array of I is 1, so we'll update array of I is 1 and we will increment that count to 1, right? So this modification you have to do. When you have to do this modification, when the count, so when the count will become 0, so let me write the code. When this modification you have to do, this modification you have to do if the count will become 0, then what we'll do, you will update the candidate variable with the array of I, and we will also set the count to 1. So this modification you have to do. This is there in the Boris-Moting algorithm when the count becomes 0. So we will update the candidate and we will set the count as 1, right? Now let's move ahead. I is here. Now see, this array of I and this candidate, which is updated candidate 1, this is not same, right? So if it is not same, then what we'll do, we will decrement the count. That is the first thing. Now when count becomes 0, what we'll do, when the count becomes 0, then we'll update the candidate with the array of I. So what is array of I? Array of I here is 2. So this 1 will become 2, right? Now this 1 will become 2, right? And the count which is 0, it will become 1, right? The count which is 0, it will become 1 because that is there in the algorithm. Now let's update I or increment I. Now see here, I is array of I here, array of I is equal to candidate. So if array of I is equal to candidate, we will simply increment our count pointer. Now count will become 2, right? And finally at I will come at the last element. Now here I is 1, but the candidate array of I is not equal to candidate. So what we'll do, we'll simply decrement the count to 1, right? Now we have traversed the entire array. So now what is the element that is left? 2 is the element is left. So now we can say that the majority element for this question is 2 because 2 is having a count 1 after traversing the entire array, right? I hope you understood the problem, right? Let me write the code for better understanding. Right, let me write the code. Integer majority element. So what is given? We have given an array, right? We are given the size of the array n. Now what we are doing, we are taking two variables. First variable is called candidate. That candidate will be initialized with array of 0, and we'll also take a count variable. That count will be initialized with 1 because the candidate is having one variable and that count is 1, right? Now what we'll do, we will traverse the array. So traversing the array, we will start from I equal to 1, I is less than n, and I plus plus, right? We'll traverse the array. What we are checking? We are checking if array of I is equal to candidate, right? This is thing we are checking, right? If the array of I will become equal to candidate, then what we'll do, we will increment the count. So count plus equal to 1, right? Else if array of I is not equal to candidate, then in what case what we'll do, we will decrement the count. We will decrement the count minus 1 equal to 1, right? This is what Moore's algorithm is saying, right? We will also check one condition, right? If the count becomes 0, then in that case what we'll do, when the count becomes 0, what was the algorithm that I told? This was the algorithm, right? If the count becomes 0, then we will do some updation. What was the updation? So if the count becomes 0, then we will update our candidate to the current array of I value, and we will initialize count, or we will update our count to 1. So this was the updation that we have to do when the count becomes 0, right? And we will end our loop, right? And then what we'll return? We will return candidate, because that candidate will be the majority element, right? So this is the entire code that to solve majority element which is present in the array, right? So this is the entire code, right? Now what is the time space? Let's quickly see the time complexity and space complexity. The time complexity will be order of n. Why? Because we are traversing the array one time, so time complexity is order of n. What is space complexity? We are not using any space, so the space complexity is order of 1, right? So this is the improvement that this Moore voting algorithm does, right? It reduces the space complexity from order of n to order of 1, because in the brute force approach we are taking order of n space when we are using hash map, but if you use this Moore voting algorithm, the space complexity becomes order of 1. Okay, I hope you understood the problem. Thank you for listening.